Hello everyone. Today we will look into the root locus method in the control system. See, this is a method to find stability of the system uh, by analyzing the movement of the poles in this plane. Okay, there are a lot of laws and rules are there for the root locus method, and I will explain that one by one by doing this example. First of all, when you are going to solve a problem, uh, start with finding the open loop poles and open loop zeros of that equation. So here the open loop zero and open loop pole is that we get a see there are no zeros in this equation when we look into the numerator of the equation, and by looking at the denominator we have open loop open loop poles. So when we look in the denominator we have 0, -3, and by solving this uh, equation we will get two more open loop poles, that is 1 plus or minus j, -1 plus or minus j. Okay, so we have four open loop poles and zero open loop zeros. Okay, so next step is to find the number of branches of this root locus. Now we have number of poles is equal to 4 and number of zeros is equal to 0. So if number of poles is greater than number of zeros, that if P is greater than Z or Z is greater than P, I'm sorry, if P is greater than Z, number of branches is equal to P. If Z, that is number of zeros, is greater than number of poles, then number of branches is equal to Z. So in the graph, plot these poles. We have a pole at 0. Poles are denoted by X mark, and we have a pole at -3. So mark here at -3 we have a pole, and also at -1 plus or minus a j, that is we have a pole here and another pole here. Okay, four poles are here. The next step is that we need to find which all sections in this uh, S plane is the part of root locus. See, the criteria for finding that region is that here this is 0. So when we look from the point here, -3, we have odd number of poles. So the thing is that when we look from point, when we take a pole and when we look into the right side of that, if we have odd number of poles and zeros, that section is in the root locus region. So when we look from the pole -3, we have odd number of poles, 1 2 3. We have 3 poles, which is an odd number. So from 0 to -3 is the part of root locus. So I'm darkening it to identify the part of that root locus. So this 0 to minus 3, the root locus is part. The section is part of the root locus. So the poles are moving in this way, like that. Okay. See, the poles need to pair up with the 0. uh, Here the 0 will be at infinity, I mean minus infinity. So when these poles are moving in this direction, that means at a point somewhere here they will meet each other and they break away from the negative real axis. That means when they collide, when two things collide each other, they will break away. Same thing happens here when these 2 points, this is coming through. uh, I'm sorry, the pole movement from here is from to the left, and here the pole movement is to the right. So at a point they will surely collide and they will break away from the real negative real axis, and that point is known as the breakaway point in the root locus method. So in order to find the breakaway point, there's a little procedure for that. First of all, we need to equate the characteristic equation of the given g of s. That means this equation, the characteristic equation of this equation, we need to equate that to 0 and find k. K is equal to minus. I solved this equation. Okay, is equal to minus of s raised to 4 plus 5s raised to 3 h squared plus 6x, and you should do the derivative of k with respect to s and equate it to 0. So this is the derivative of the equation that we have for k. Solve this equation and find values for s. So these are the values for s, that is minus 2.28 and minus 0.73 plus or minus 0.348. So which will be the breakaway point? So we need to find that which among the value of s is the breakaway point. In order to find that, we need to put this value or the substitute the value of s in the equation of k. That means k is equal to minus of s raised to 4 plus 5s raised to 3 8x squared plus 6x, that equation. We need to put this value of s in that equation, so and find and check whether the value of k real and positive. So when so first of all, start with minus 2.28, and when we substitute minus 2.28 for us, we get a positive and real value. So that's a breakaway point. Minus 2.28 is a breakaway point, and we should consider this point too. But by substituting this as s in the equation, the value is not real and positive. So the breakaway point is minus 2.28, but that's not enough. We need to find how this line break away from the real axis, whether it is 90 degree or it is or it is whether it is slanted by 30 degree, 45 degree, 60 degree, or in what angle does it depart from the negative real axis. First of all, mark the breakaway point here, that is minus 2.28. It will be something right here. Sorry, but it's a little bit dirty. I'm sorry about that. It will be minus 2.28 on the breakaway point. So, that's the breakaway point. And as I said earlier, we need to find the direction of this movement of the poles from the breakaway point. In order for that, we need to find the centroid, the centroid of the asymptotes. See, You all are familiar with the word asymptote. The distance between this asymptote and the curve became zero at infinity. So we need to draw an asymptote in order to draw this movement of pole from that breakaway point. So the equation to find the centroid of the uh, asymptotes is the here is the equation, sum of real part of poles minus sum of real parts of zeros divided by number of poles minus number of zeros. By the way, we have no zero here, so add the poles, add the real part of the poles and divide it by the number of poles. After all our calculations, we get the centroid as minus 1.25. So mark it in the graph. Okay, I'm going to mark the uh, centroid minus 1.25, right? Maybe it will be maybe here minus 1.25. That's a centroid where the asymptotes pass through, and we need and now after that we need to find the angle of the asymptote. So this is the equation for finding the angle of the asymptote, 180 into 2k plus 1 by p minus z. Okay, see this k ranges from 0 to 3. That means the number of branches that root locus have: 0, 1, 2, 3, 4. 4 numbers. Okay, so at k is equal to 0, the angle equal to 180 divided by 4, that is equal to 45 degree. Similarly, for k is equal to 1, angle is equal to 135 degree, and for k is equal to 2, angle is equal to 225 degree for k is equal to 2, and for k is equal to 3, angle of the asymptote is 315 degree. So mark this in the graph. So you have drawn already these asymptotes here. See, first of all we need to take that 45 degree for k is equal to 0 from the centroid that we have already done before. So take the 45 degree. So make sure that you are taking the angle from the positive side, okay, from the right side. So 45 degree and taken 135 degree, okay, 135 degree and 225 degree and 315 degree. Okay, see, I guess now we all understand how the centroid is drawn. Sorry, the asymptote is drawn through the centroid, and now we are going to uh, draw that pole movement from the breakaway point. See, this curve should be in order to meet the asymptote at infinity. So only in that way the curve should be drawn from the breakaway point. So this is how it is drawn. Okay, from the breakaway point it draw like that it is going to meet the asymptote at the infinity. Okay, draw like that. And now we have one, two root locus region, and there is additional two more to come that we have already found out at the beginning of this problem. That is the number of poles is equal to the number of branches of root locus. There is two more branches that need to be drawn, and that is from the complex pole that we have marked right here. That is minus 1 plus j and minus 1 minus t. So how the poles varies from this complex pole. For that, we need to find something called the angle of departure, and the equation to find the departure uh, of the pole is 180 minus 5p minus 5z, and there is a new term come here, that 5p and 5z. See, what is this 5p and 5z? So I'll explain that by looking into the graph. Okay, join every other poles, that is 0, minus 3, and this comes up pole right here to the one of the imaginary pole minus 1 plus j, and find the angle for that. So when we join 0 to minus 1 plus j, that is minus 1 plus j, uh, uh, the angle here is we should measure using the protractor. This is 5p1, that's a 5p1 angle here, and this is a 5p2. At a closer look, we can assume that 5p2 is sorry, not assume, it is sure that 5p2 is 90 degree, and we need to find the 5p1 using protractor. It may be nearly 135 degree or 130 degree, and also this angle right here, this is 5p3, 5 5p3, 5p3. Now this I'm sorry that the little bit clarity is less here. Okay, whatever, find that 5p1, 5p2 and 5p3 using protractor, and add them all and you get 5p. In my graph, 5p1 is 130 degree, 5p2 is 90 degree, and 5p3 is 30 degree, and the total sum of these pole angles is over 250 degree. So put that in the equation and find the angle of departure of the complex pole. Angle is equal to 180 minus 250. See, 5z is 0. Okay, 180 minus 250, that is 70 minus 70, that is minus 70 degree. See, we found what we found out here is the angle of departure uh, of minus 1 minus j, that is from minus 1 minus j. Okay, I'm sorry, what we have find now here is the departure of complex pole, that is minus 1 plus j is the angle of departure from minus 1 plus j. So from minus 1 minus j, it is 70 degree. And this is how the final piece of jigsaw is done. These are the last two branches of the root locus, that from the angle of departure. If we have the from minus 1 plus j, I took minus 70 degree, and from that I just turned to here, because this is the imaginary axis crossing point. I will explain how to find the imaginary axis crossing point after this. And here, this is imaginary axis crossing point, and I turn this root locus, not me, that is the system 2, the movement of poles in the system 2. The poles will move from in this direction as the asymptote is passing through here. So and that's about all about the root locus drawing about this equation, and to find the imaginary crossing point, to find the imaginary axis crossing point, consider the characteristic equation. Okay, we consider the characteristics equation and substitute j omega for s in the equation like this: j omega raised to 4, 5 j omega raised to 3, and so we get like this solving equation omega minus, and equate the imaginary part of the equation with 0, and we will get that value of omega, that is plus or minus 1.09, and that is the imaginary axis crossing point. Yes, one, we need to add j uh, for that, that is plus or minus 1.09 j. Thanks for watching.